This is FE Peer Review, the Flat Earth Peer Review channel. The date is October 7th, 2020. The video in review is by Rachie 00000. The URL for the video is below. I'm going to do this as a kind of a slideshow in response to Rachie's video in which she points out that the coins on the floor of her hallway appear to disappear as she lowers the camera to the floor. Why might the coins disappear on an apparently flat surface? There are a number of reasons. I'm generalizing here beyond coins on the floor of the hallway. First reason could be atmospheric interference such as fog or mist. Second reason could be lens, focus, depth of field, issues with the camera. A third reason could also be the resolution of the camera image. Fourth could be irregularities in the floor surface. 5 could be related to Rayleigh criterion. Now it may be any or a combination of these or something else that I have not included here. I'm not attempting to create an exhaustive list. Mists and fogs affect target objects uniformly over their areas, not from the bottom up. As you can see in this photograph, a boat sailing into the mist is not going to appear to disappear from bottom up, but rather just sort of fade away. So we can pretty well rule mists out. Obviously, in the case of the coin in the hallway, we can rule it out, but even when discussing distant objects moving far away from the viewer, mists do not function in a bottom-up manner. Here's a view of the hallway. I've taken the liberty of reorienting the photograph to the horizontal. And yes, the coins are out of view. What we do see is a number of issues related to the focus of the camera. I'm assuming this is some kind of a smartphone, iPhone, something like that. And it appears to be struggling to focus in different areas. We see a nice crisp line in the door frame. We see on the left door frame, we see a crisper line. Down here at near the floor, the lines are very fuzzy and unclear. The camera is unable to get any detail in the floor itself. You can see the joints in the floorboards, but they're very thick and out of focus. So this surface, which is at a very steep angle compared to the camera, is not coming into focus, whereas the surfaces that are facing the camera more closely are better focused. Now, I'm not exactly sure how the lens on a smartphone type of camera works, but this is a diagram that explains some things about traditional camera lenses, including digital cameras as well as the old-fashioned film cameras. The lenses have an aperture, which is an opening, and you can vary the size of the opening of your lens, as you see in this top diagram. The advantage of a large opening is it lets a lot of light in fast, which means you can get a better picture. You can get a picture faster or when they're in a darker space. So the result, though, the trade-off with the size of the aperture is what they call depth of field. So, for example, a person in the foreground will be in focus, but the stuff in the background will be out of focus. That's when you have a large aperture. If you go to the right side and look at the opposite extreme, a very small aperture, you can get both the person in the foreground and the objects in the distance in focus. That's depth of field, and that's controlled by the aperture. So there are photographic reasons for where you might want to fall in this spectrum. A portrait, for example, if we look at the left image, a portrait may be taken using the left approach because the background is supposed to just be complementary to the focus, which is on the person. Another example, other extreme, would be a photo of a tourist in front of a landmark. The person wants his picture taken in front of the landmark, and he wants to be able to see the landmark nice and clear, so you want both of them in focus. So that's aperture and depth of field, and there seem to be similar kinds of issues going on in this image here. Like I said, I haven't learned how the phone cameras work, but it does appear to be having a similar depth of field type of issue. So that's obviously affecting what we see. in this picture, the limitations and the nature of the technology being used to take the picture. We have to remember that whenever we look at anything ourselves with our eyes, we're seeing what our eyes see. But the moment we want to communicate that to somebody else visually, we have to take a picture of it. We are no longer seeing it with our eyes, we're seeing it through a camera. So what we're actually showing the other person is not what we saw, but what we saw through the camera. In fact, what the camera saw. It's important to keep that in mind as we share images with each other. But let's look at the coin in the hallway example just a little bit more and extend it to outdoor observations. So the coin, I want to get a proportion, the length, the thickness of the coin relative to the length of the hallway. That hallway looks to be about 15 feet long. The coin is about 3/32 of an inch thick. So that makes the ratio of those two numbers 1 to 1,920. In other words, if you were to stack 1,920 coins, they would be the same length as your hallway. Let's compare that to a person standing at a beach looking out to sea. Let's suppose the person's eye level is 6 feet off the ground. At 6 feet off the ground, they'd be able to see 3 miles, 15,840 feet. Referring back to that ratio of 1 to 1,920, that means that a wave on the water, or a wave in swell, or a swell would of a height of 8¼ feet would be the equivalent thickness to the coin in the hallway. So a person standing on the beach seeing an 8-foot wave would be seeing an object that is proportional to the view of 3 miles as the coin is to the 15-foot hallway. Consider possible irregularities in the floor surface compared, for example, to waves on the sea. So we've looked at the wave there, an 8-foot wave out in the distance on the sea. Is the hallway floor perfectly flat and level, or might there be irregularities in its surface? An easy way to test is to hold a 6-foot-long builder's level to it, one with a well-machined straight edge. I have one of those at my house. It's 6 feet, 2 meters long, nice aluminum, solid aluminum level with a good straight edge. Hold something like that to your floor, and you'll see pretty quickly exactly how flat it really is. And I don't mean level, just plain flat. I just use the example of builder's level because they're usually made very straight. 3/32, that's less than 1/8 of an inch. 1/8 of an inch in standard construction of good quality is fine for a floor, for variations in a floor surface. I'm not talking about, like laboratories and things like that, but just people's homes. That's good quality work to be within 1/8 of an inch. I worked in construction all my life, and that is actually a standard. 1/8 of an inch is a standard cutoff point. Anyway, let's move on here. Can we expect to see swells and waves of 8 feet on the sea? Absolutely. Can we expect to see slight variations in the flatness of a floor? Yes, we can. Conclusion: irregularities in apparently flat surfaces could conceal the lower portions of objects from view. I should say right off the bat that I'm entirely convinced that there could be reasons why objects might disappear from bottom up, even on a flat or a globe earth. So that in itself is not really a proof. You need to go into it in further depth, and that's what we're going to do next. However, can these irregularities cause objects to disappear entirely and from the bottom up? Yes, but only under specific conditions dependent on the observer height, the blocking object height, and the blocked object height. We're going to move on to a few diagrams that I've put together that I think might help explain some of these conditions that are involved with this kind of observation. I've created a few slides here, and what we've got is an observer, which is this red triangle on the left. We've got a target object, which is this tall green triangle on the right, and then we will have blocking objects, which are blue triangles in various places and of various sizes. Let's start by looking at the top diagram here. Let's move this where it's best. There. We have the blocking object is smaller than or lower than below the eye level of the observer. This is over in the upper left corner of the screen. And at the upper right corner, we have a target object. And what we see in this dashed line is the line of sight of the observer. And it's blocked by this blocking object, which covers the bottom of the target, comparable to its own height, approximately its own height. If we're right up against it, it would be its own height. Now we look at the blocking object on the left, very close to the observer, and we see that it does not block the target object. It blocks the water immediately behind it. I'm saying the water. This is a person standing on the beach. This is a wave. The water behind it is blocked up until here, at which point the observer can see over the wave the rest of the water to the target. So what we see is that the blocking object, when it is lower than the eye level of the observer, can only block its own height of the target object. It can't block more than its own height of the target object on a flat earth, on a flat plane. Now let's look at a blocking object that's higher than, taller than the observer, that goes above the observer's eye level. When the object is close to the observer, it can block a great deal of the target, much more than its own height. When the blocking object is far away from the observer, it blocks only its own height. So what we see here is that the blocking object will never block less than its own height. It will block more than its own height, and that depends on it being close to the observer. Let's look at another example where we move the observer relative to the blocking object and the target. Here's the object, the target, the blocking object, and the observer. The dashed line shows that when they're close, the blocking object blocks less. As the observer moves farther away, the amount, it's a very small difference, but in this particular diagram, but you can see that as the observer moves farther away, the dotted line shows that more of the object is blocked. However, the blocking objects will never block more than its own height, so long as it's below the eye level of the observer. Take a look at another example here. We've got the observer, the blocking object, and they're close together, and it's blocking nothing of the target. Again, as the observer moves further away, the blocking object blocks some of the target, and so in this case, as the observer were to move away, the target object would be blocked from bottom up, but never more than the height of the blocking object. Let's go on to the next slide. Now, let's talk about wind turbines out at sea. Here we've got somebody standing on the beach, 22 meters up above the beach. And off in the distance there's a wind turbine. And between the person and the turbine there's a big wave, higher than the observer. That wave will block a good chunk of that turbine. Now let's go down to the next image. Suppose there's a second row of wind turbines after the first one, farther away. We can see that even more of that turbine is going to be blocked. And then there's a third row, and even more of that one is blocked. And a fourth row, even more of the fourth row is blocked. So what we're seeing is the farther away the turbines get, the more they disappear from the bottom up. However, that depends on one very important factor. The blocking object has to be higher than the observer. Rayleigh posted a video recently of somebody else's bit of film footage. I don't remember who was right at the moment, but we see wind turbines. They've got this particular chunk at the bottom here, which makes it very easy to see how much of the bottom is being blocked. Here we see a further distant turbine and more of it's blocked. And here we see yet further away, that whole bottom piece is completely gone. So what we're seeing is turbines with their the bottom portions disappearing. They're disappearing from bottom up. However, that only works if whatever is doing the blocking is taller than the observer. And we were told by Rayleigh that the observer was 22 meters off above the water line. So that means there have to be waves of 22 meters, waves and swells of 22 meters in order to cause blocking on a flat plane in that circumstance. And a wave or swell of 22 meters would be utter catastrophe, a tsunami basically, a small tsunami, wiping out coastal communities, which was not what was happening when that image was taken. So there's something more to it than meets the eye. Let's look at what happens when the blocking object is lower than the observer. Here's the observer at 22 meters. Here's the first wind turbine. Here's the blocking object. It indeed blocks some of the turbine. Now we go to the second row of wind turbines further away. The blocking object still blocks some of that turbine, but less than the first one. We go to the third row, a little bit of that one is also blocked, but yet less than the second or the first. And finally, we look at the fourth row, and we can see all the way to the bottom of the turbine. So when the blocking object is lower than the observer, the farther away the turbines get, the more we can see of them. They're not disappearing from bottom up, they're appearing from bottom up as they get further away. And that's what happens on a flat surface when the blocking object is lower than eye level. So let's back up to this. So if this view we got from Rayleigh contains a 22 meter plus wave, I'm sorry, but I don't see it, and I didn't hear any news about Liverpool and Blackpool being inundated by a tsunami. So don't think there was a 22 meter wave in there. If there wasn't a 22 meter wave, then on a flat Earth we should be seeing more of the distant turbines than of the close turbines. I say more of the turbine, I don't mean that they will look bigger. They will look smaller because they're further away, but we will see all the way to the bottom of them, whereas the closer turbines would be blocked. So there's summary, the tall blocking wave, the small blocking wave. And I went into, in another video I went into this video of Rayleigh's and did a little bit of measuring. Rayleigh had given the dimensions of these wind turbines that he'd gotten from another website. And what I'm saying here is based on what he said in his video. I'm going from memory, however. So as I recall, the pylons on these turbines were 98 meters tall, and the blades themselves were something like 53 meters. So from the center point of the turbine where the blades come together to the point where it hits the water, to the bottom of the pylon at the water line is 98 meters. And the blade, I've drawn a red line over this blade. The blade is 53 meters. So what I did was I took this 53 meter blade as an example for this particular turbine. And I rotated it, I copied it and rotated it so it was straight up and down to give me a kind of a ruler to measure. And then I made 10 meter marks for 5. So there's 50 meters and another little bit for the 53 meter blade. And then I continued with the 10 meter marks until I got down to 100 meters. And the base and that pylon is 98 meters high. So the bottom of this pylon is down here somewhere below the horizon line. That's one of the pylons that's further away, one of the wind turbines that's further away. You can see there's a few that are even further back, and some of them, you can see their blades actually appearing to hit the water line as they rotate. So we've got wind turbines that are disappearing below the horizon as they recede, which can only happen on a flat plane if there is a blocking object that's higher than the observer. In this case that Rayleigh provided, the observer is 22 meters high. There was no way there was any blocking object on that water surface between the observer and those turbines that was 22 meters high. It would have been a major catastrophe. If there were blocking objects that were lower than the observer, we would see the opposite of what we are actually seeing in the image. We would be seeing that the turbines further away that we can see the bottom of the turbines that are further away, and that the turbines in front would be blocked. So this image does not fit either of these scenarios at all. If the surface is flat, the blocking object can either only be higher or lower. And this image does not match either of those situations. Let's take a quick look at what would be seen. I'm putting this here because I want to point out something about how we can start to organize the way we observe these things in a productive manner. I mean, you need to gather data, but you also need to gather relevant data. And you need to know what kind of data you're going to try to gather in order to be able to draw a conclusion from it. So I used Walter Bislin's curve calculator for this. I put an observer height of 22 meters and a target distance, which I varied. And then all I did was I simply used the calculator to say at that height, at 17 kilometers, the hidden height of an object, it doesn't matter how big the object is, the hidden height of the object is 0. At 17 kilometers, at a 22 meter observer height, you can see the base of the object. And this is with no atmospheric refraction. This is just pure geometry on a sphere. I'm not going to complicate it with refraction for the time being. If we need to go further with this, we will. At 17 kilometers, we can see the bottom of our object. At 17 and a half, the bottom starts to get concealed a little bit, tiny bit, 45 centimeters. At 18 kilometers, it's, I said 45, it's 4.5 centimeters, 45 millimeters, 0.045 meters. At 18 kilometers, it's 124. At 19 kilometers, it's 399. 20 kilometers, it's 833. 21, it's 1.42. So basically what's happening is more and more is being hidden as the distance increases, but not just linearly, it's increasing, what's the word? I want to say parabolic. Not exactly parabolic, but I've charted it here. Basically, from 0 to 17 kilometers, nothing is hidden, and then we start to get some hidden, and then more hidden and more, and it gets faster and faster as the object moves away from us. So that particular parabolic aspect of the way the object is being hidden is important. It's not being hidden linearly. It doesn't disappear 8 inches each time the boat moves another mile, and then another 8 inches or the next mile. It's not like that. It's not a linear disappearance. It's sorry, I'm having a hard time remembering the word. It's this parabolic function is what we're getting. So if you wanted to do a real observation that would allow you to come to a conclusion about whether or not the bottom-up disappearance has to do with a curved Earth or some other factor, this would be a very powerful kind of observation to make. Get yourself up above any possibility of local influences such as waves and swells. Get a boat going out towards the horizon and track the distance of that boat from your point. If you could ideally have somebody out there on the boat in communication with you and tracking their location relative to you, then as they move beyond the horizon, if they disappear from bottom up in this parabolic fashion, as opposed to a linear fashion, it would be a very strong indicator that they're moving over a curve. If it happened in a linear fashion, then you'd need to look for some other kind of reason why it's disappearing the way it is. So that's the way you could organize a real observation from which you could draw some very convincing conclusions. I want to move on to one last thing here, Rayleigh criterion, which comes up from time to time. Rayleigh criterion has to do with, in brief, angular size. Light has waves, and it passes through our eye in the form of waves, and consequently there are geometrical limitations to what we can see. When the angular size of something becomes very small, we can no longer differentiate its parts. Doesn't matter whether it's a grain of sand or a skyscraper. Stand on the beach and look down at your feet and you may be able to make out individual grains of sand, but look 20 feet down the beach and you won't be able to make out individual grains of sand even though they're only 20 feet away. Whereas you can easily see the boulder that's 100 feet away or the cliff that's a mile away. So just because it's far doesn't mean you can't see it. It has to do with the angular size. So Rayleigh criterion, coin in the hallway example, the angular size of the edge of that coin from 15 feet down the hallway is 0.03 degrees. That was done with just a simple triangle calculator online. You can check that if you want. There's a nice video on YouTube that explains the Rayleigh criterion in detail fully with respect to the eye, because the actual number from the Rayleigh criterion changes depending on whether it's an eye or a camera lens or telescope, But for the human eye, this nice video here explains how it works and what the answer is, the minimum angular size that a normal healthy human eye can perceive, and that number is 0.00874 degrees, which, as we can see, is considerably less than 0.03. So I just brought this up because we can rule out Rayleigh criterion as a reason why that coin disappears at the end of the hallway. We are well within the range where we should be able to see that coin at the end of the hallway. So it's not some kind of Rayleigh criterion effect. That pretty much wraps it up here. My point in doing this was not to try to make a debunk or a rebuttal to your video, but rather just to point out all the different ways in which we can look at the issue of seeing something at a distance and all the different factors that are involved that we have to consider as we're doing that. Our tools have limitations, our tools being our eyes, also our tools being our cameras, a cell phone camera as opposed to a digital camera. Every tool has its limitations, and we have to know what those limitations are in order to use the tool to its maximum effect. So given these various ideas I've put out here, I hope that you find this useful and will be able to refine your observations further. And please do more of them. And it's great that you're putting them out there online for people to see. They don't all need to be out there. If you just keep on making them and thinking about them, you'll already be learning a lot. That's the end of this video. Thanks for your patience as I ramble through this. I was kind of rambling at the end of the day, and I wanted to finish this tomorrow, but decided to push through. So again, thanks for your patience. I hope you liked it, and I hope you'll click that like button and subscribe if you haven't already. Have a great evening.